Good afternoon, everyone. Can you hear me?
Yes, sir.
Okay. So this is Anshuman Das from India, and I'll be chairing session 3B. So please note one thing that session 3A is being held in another link. So if anyone here is from session 3A, you can join that link, particular link for 3A, and this technical session 3B will be conducted in this link. So I'll be starting in a minute. So mainly we are having a few papers here, mainly on graph theory, some on dynamical systems and cryptography. So the first speaker of the session is S. Shindumal, and the title of her talk is Leverage Centrality on Corona Product of Some Graphs. So I would like to request her to present the screen and start it. And just one announcement that as because we are having a number of papers here, so the time will be 10 minutes per speaker and 2 minutes for any question and answers. Okay, let's start. So I invite the first speaker.
Okay, sir. May I start now, sir?
Yes, you can start.
Okay, thank you, sir. Whether my presentation is visible, sir?
Yes, but you can make it full screen.
Full screen.
Yeah, just go to view.
Yes, sir.
On the top left, go to view. No, not there. I mean, okay.
Okay, sir, I am trying to take.
Okay. Try.
Sir, some problems are there. My PPT is not working. This is my PDF, sir. Whether it is okay, sir? Hello, sir?
Yes, it's okay. It's okay. You can
Okay.
start with this.
Okay, sir. Okay, sir. Myself, Sinimolas, working as an assistant professor in TK Madhav Memorial College, Nangargulangara, Kerala, doing PhD under the guidance of Dr. Sunil Kumar R, Associate Professor, BGM Government College, Chavara, Kerala. Sir, is it visible now?
Yes.
My topic of presentation is leverage centrality on corona product of some graphs. This is my outline of presentation. First of all, leverage centrality, a leverage center, corona product of two path graphs, then cycle graph and a null graph and a cycle graph and a path graph and a cycle graph, and then conclusion and finally references. The definition of leverage centrality. A leverage centrality is a measure of the relationship between the degree of a given node V and the degree of each of its neighbors Vi, averaged over all neighbors Nv, and is defined as L of V is equal to 1 by degree of V summation degree of V minus degree of Vi by degree of V plus degree of Vi, where Vi varies over all neighbors of V. The next definition of leverage center. The leverage center of a graph G is defined as the set of nodes having the highest leverage centrality in the graph. Unicentric and bicentric leverage graphs. Unicentric leverage graphs are those graphs with unique leverage centers. And bicentric leverage graphs are defined as those graphs with exactly two leverage centers. Now the corona product of graphs. The corona product G composition H of two graphs G and H is defined as the graph obtained by taking one copy of G and mod V of G copies of H and joining the ith vertex of G to every vertex in the ith copy of H. This is the notation we used in this. The vertices of the graph G of order n be labeled as u1, u2, etc. un, and that of the graph H of order m be labeled as v1, v2, etc. vm. In the graph G composition H, the vertex vk in hi is denoted by vik, where I varies from 1 to n and k varies from 1 to m. Now we move to the corona product of two path graphs. This is a theorem. Let G is equal to Pn and H is equal to Pm, where n m greater than or equal to 5 and n less than or equal to m, or n greater than or equal to m. In the corona product G composition H, all the vertices V1K in the copy H1 have the same leverage with the corresponding vertices Vnk in the copy HK, where K varies from 1 to m. Furthermore, the corresponding vertices in the remaining copies I varies from 2 to n minus 1 have the same leverage. Also, G composition H is a bicentric leverage graph with U2 and Un minus 1 as leverage centers. Now, cycle graph and a null graph. That is, we move to the leverage centrality analysis of the corona product of a cycle graph and a null graph. First of all, the definition of a regular cyclic caterpillar. Let G is equal to Cn be a cycle graph on n vertices where n greater than or equal to 3, and let H be a null graph on m vertices m greater than or equal to 1. Then the corona product G composition H will be a regular cyclic caterpillar Cnm. We continue with some definitions. A unicyclic graph C is called a cyclic caterpillar if the deletion of all its pendant vertices reduces it to a cycle. And a regular cyclic caterpillar CNM is a cyclic caterpillar with the m vertices attached to each vertex ui. I varies from 1 to n of the parent cycle Cn. Now this is the theorem. Let G is equal to Cnm, where n greater than or equal to 3 and m greater than or equal to 1 be a regular cyclic caterpillar of order n plus nm. Then for V in G, we found that the leverage centrality of V is equal to m into m plus 1 by m plus 2 into m plus 3 if V is a node of Cn, and this is equal to minus m plus 1 by m plus 3 if V is a pendant node. Now, the leverage centrality analysis of the corona product of a null graph and a cycle graph. Let G star is equal to H composition G, where H is a null graph on m vertices and G is equal to Cn. Then for V in G star, leverage centrality of V is n minus 3 by n plus 3 if V is a node of H, and minus of n minus 3 by n plus 3 if V is a node of G. We know that as a null graph and a cycle graph are whole-centric graphs, even though its leverage centrality analysis of its corona product is an n-centric graph. Now, cycle graph and a path graph. Let G is equal to Cn be a cycle graph on n vertices where n greater than or equal to 3 and H be a path graph on m vertices m greater than or equal to 5. The vertices of Cn be labeled as u1, u2, etc. un, and that of the path graph on m vertices be labeled as v1, v2, etc. vm. In the graph Cn composition Pm, degree of ui equal to m plus 2 for 1 less than or equal to I less than or equal to n. Here the vertices in the copies I varies from 1 to n can be classified as type 1 is degree of E equal to 2, and type 2 degree of E is equal to 3 and is adjacent to the nodes of degree 2, and type 3 as degree of E is equal to 3 and is not adjacent to the nodes of degree 2. This is the theorem. Let G star equal to Cn composition Pn where n greater than or equal to 3 and m greater than or equal to 5. Then for V in G star, leverage centrality of V is found to be 1 by m plus 2 times m cube plus 3 m square plus 8 by m plus 4 into m plus 5 if V is a node of Cn, and minus of 3m plus 2 by 5 times m plus 4 if V is a node of type 1, and 2 times 5 minus 2m by 15 into m plus 5 if V is a node of type 2, and minus of m minus 1 by 3 times m plus 5 if V is a node of type 3. And now we know that the corona product is not commutative, so we calculate the leverage centrality analysis of the corona product in the reverse order Pm composition Cn. The path graph on m vertices be labeled as v1, v2, etc. vm, and let the vertices of Cn be labeled as u1, u2, etc. un, where m greater than or equal to 5 and n greater than or equal to 3. In the graph PM composition Cn, degree of Vi equal to n plus 1 for I is equal to 1 comma n, and degree of Vi equal to n plus 2 for I varies from 2 to n minus 1. Here the vertices in the path PM m greater than or equal to 5 can be classified as type 1, that is degree of E equal to n plus 1, type 2, degree of E is equal to n plus 2 and is adjacent to the nodes of degree n plus 1, and type 3, degree of E is equal to n plus 2 and is not adjacent to the nodes of degree n plus 1. And here is the theorem. Let G star equal to PM composition Cn where m greater than or equal to 5 and n greater than or equal to 3. Then for V in G star, leverage centrality of V is equal to 1 by n plus 1 times minus 1 by 2 n plus 3 plus n times n minus 2 by n plus 4 if E is a node of type 1 by n plus 2 into 1 by 2 n plus 3 plus n times n minus 1 by n plus 5 if E is a node of type 2, n into n minus 1 by n plus 2 into n plus 5 if V is a node of type 3, and minus of n minus 2 by 3 times n plus 4 if V belongs to Cn adjacent to type 1, and minus n minus 1 by 3 times n plus 5 if V belongs to Cn adjacent to type 2 or type 3. This is the corollary. In PM composition Cn, m greater than or equal to 5 and n greater than or equal to 3. This is a bicentric leverage graph. And this is the conclusion. The leverage centrality analysis of some graphs on corona product is done. In each case, the leverage type, the number of distinct leverage centralities are also identified. These are my references, and that's all about my presentation. Thank you, sir.
Thank you. So we have 2 minutes for any questions. If the audience have any questions, they can ask now. Any question from the audience? Okay, if not, I would like to ask one thing, that what is the physical interpretation of this new concept of leverage centrality? I mean, is there any physical behavior which is represented by this?
Yes, sir, of course. This leverage centrality is especially designed for brain networks, sir. In order to find a network hubs in our brain, we can use this centrality.
Okay. Thank you. Thank you.
Okay, sir. Thank
So
you.
with that, we'll pass on to our next speaker. The title of the talk is on some degree-based topological indices of the zero divisor graph of reduced rings, and the presenter will be P. Gangeshwari. So I'd like to ask you to present your screen.
Good afternoon, everyone. Sir, my screen is visible?
Yes, it's visible.
Okay.
Please.
Myself, P. Gangaishwari, research scholar from Mananmaniam Sudarnar University, Tirunelveli. I am working under the guidance of Professor K. Selvakumar, sir. Today, my topic is on some degree-based topological indices of zero-divisor graphs of reduced ring. Okay, I hope everyone know the definition of zero divisor. Let R be a commutative ring. A non-zero non-unit element A is said to be a zero divisor if there exists another element, non-zero non-unit element B, such that their product is zero. Actually, I'm working in the field area of algebraic graph theory. We usually associate a algebraic structure to a graph, and we study the algebraic property by using the graph theoretical approach. Now we consider a zero divisor graph. Let's see the definition of zero divisor graph. Let R be a commutative ring with unity. Zeta R star be the set of all non-zero non-units, non-zero zero divisors of R. The zero divisor graph of R is denoted by gamma of R. It is a simple graph. Two vertices of gamma of R are adjacent if their product is zero. Here is an example for zero divisor graph. Consider the ring Z5 cross Z2. The set of all non-zero zero divisors of R given by this set. The corresponding zero divisor graph is this one. We can notice that product of these two elements is zero. So here we are giving the adjacency. Here is also the product is 0, so here we give the adjacency. Next definition, Hatch-join operation of graphs. Actually, one of my teachers said mathematics is a collection of tools. If you use the correct tool at a correct place in an efficient way, we can do the things easily. Here we use the tool called Hatch-join. It reduces my work in an amazing way. Let's see the definition of Hatch-join. Let Hatch be a graph with a vertex set V. V contains 1, 2, 3 up to K, and G1, G2, Gk be the collection of graphs with respective vertex sets Vi equal to Vi1, Vi2, and so on, Vini, where I varies from 1 to K. For example, the graph G3 has the vertex set V31, V32, and so on, V3N3. Please note that my graph H has K vertices, so I am taking K graphs here, collection of K graphs. Here Hatch-join is denoted by, Hatch-join graph is denoted by H of G1, G2, and so on, Gk has vertex set V1 union V2 union Vk. If you pick two vertices, there are two choices, right? The two vertices from the same factor graph or the two vertices from the different factor graph. Suppose the two vertices VIP and VJP, here is a mistake, VJQ. Suppose the two vertices from same factor graph, that means I equal to J. Suppose the two vertices are adjacent in that factor, then in Hatch-joins also they are adjacent. Suppose the two vertices are not adjacent in that factor, then Hatch-join also they are not adjacent. Suppose if you take taken two vertices from different factor, that means I not equal to J, then you should go to the graph H. In H, I and J are adjacent, then they are adjacent in Hatch-join also. This is the definition of Hatch-join. Here H is known as base graph and GIs are known as factor graphs. Here is an example for Hatch-join. Here we take H is P3, path with 3 vertices. So I took 3 factor graph G1, G2, G3. This is the Hatch-join graph. If you see that these two vertices from the same factor, that is the factor G1. In G1, these two are adjacent. So in Hatch-join also, these two are adjacent. If you consider these two vertices from same factor G3, in G3 they are not adjacent. So in Hatch-join also they are not adjacent. If you pick these two vertices from different factors G1 and G2, so you should go to the graph H. In H, first and second vertices are adjacent. No? So here is also you should give the adjacency between every vertex of G1 to every vertex of G2. So this is the example for Hatch-join operation of graphs. So basically I'm going to calculate the degree of the graphs. So instead of calculating degree in the big graph, I'm going to visualize this big graph as a Hatch-join of these 3 graphs. So it is enough to calculate degree in H and G1, G2, G3. Especially in reduced ring case, we proved that these factor graphs are totally disconnected. So in reduced ring case, it is more simple to calculate the degree in H. So our work is more simpler. So using Hatch-join operation, our work is very simple. This is the main idea of our work. Consider the first example. This one is the Hatch-join of K1 and K2 bar. Here H is K2. Mainly we concentrate on subrub indices of graphs. The first subrub indices is denoted by M1 of G. Second subrub indices is denoted by M2 of G. M1 of G is nothing but sum of squares of degree of every vertices. M2 of G is nothing but sum of product of degree of every pair of adjacent vertices in the graph G. So we are going to visualize zero divisor graph of reduced ring by using H join techniques. Then we are going to calculate the we can calculate any degree based topological indices. Okay, let R be a arbitrary finite commutative ring. We define a equivalence relation tilde on z of R star. Z of R star is nothing but set of all non-zero zero divisors of R. Any two element x and y are related if and only if annihilator of x equal to annihilator of y. Annihilator of x is nothing but set of all a belongs to R such that ax equal to 0. This equivalence relation form a partition on z of R star. So we get some equivalence classes, right? We name it by C1, C2, Ck. Pick one element from every equivalent classes, call it as representatives, name it as small c1, c2, ck. Then z of R star is disjoint union of Ci. We call this equivalence classes by equi-annihilated classes of gamma of R. Also, in my case, I am considering only reduced ring. So any reduced ring can be written as a product of finite fields. So R can be written as product of fq1 and so on fqi, where fq1 is a qi is a field with qi elements. Consider this set rho of k. Rho of k is nothing but set of all proper subsets of the set bracket k. Bracket k is set of all set contains 1, 2, 3 up to k. We define a characteristic vector on every element a belongs to rho of a. 1a is the characteristic vector. 1a is nothing but set of k tuple in R as a1, a2, ak, where a is 1 if I belongs to a is equal to 0 otherwise. So for any a belongs to rho of k, we define a characteristic vector. Also, we define a class Ca. Ca contains set of all k tuples where k tuples where a is non-zero if I belongs to a, otherwise it is 0. We also proved that annihilator of A equal to annihilator of B if and only if support of A equal to support of B, where support of A is nothing but collection of that position where A is non-zero. We define the equivalence relation, right? Clearly, we note that the equivalence classes are nothing but these CAs. The CAs is these CAs. Ca contains k tuple where a is non-zero when I belongs to capital A. So this a1 is picked from the first field. First field contains q1 elements, right? So it can be filled in q1 minus 1 ways because this field contains q1 minus 1 number of non-zero elements. So this can be chosen in q1 minus 1 ways. Similarly, second element can be chosen in q2 minus 1 ways. Up to last element can be chosen in qk minus 1 ways. So the cardinality of Ca is product of cardinality of Ca is product of qi minus 1. Also, a is taken from rho of k. Rho of k is proper subset of the set k. So a can be chosen in 2k minus 2 ways. So there are 2k minus 2.
You have 2 minutes left.
Okay, 2k minus 2 ways. So any zero divisor graph can be visualized as a H join graphs. We define a degree. So degree of a vertex is nothing. Degree of a vertex in H is nothing but the vertex 1b, where 1a and 1b are adjacent. The characteristic that means a 1a dot 1b equal to 0, a intersection b equal to 0. So summation cardinality of C of B. Cardinality of C of B, we already know that pi of qi minus 1. So we find out the degree. Already we know that m1 of G is nothing but sum of the square of the degrees. Just substituting, we get m1 of g and m2 of g. M2 for m2 of g also we are substituting the degree only. So this is our example. Thank you. This is my reference. Any questions?
Thank you, Angashwari. Is there any question from the audience? Okay, in absence of any question, let's thank the speaker and we pass on to the next topic or the next talk. The title of the talk is Hyperbolic Iterated Function System in Light Waves Using Graph Theory, and the presenter is M. Razi. I would like him to present her screen. Razi Gurudev, yes.
Sir, shall I start?
Yes, you can start. You can start.
Good afternoon. Myself, Dr. M. Raji, Assistant Professor, Department of Mathematics, Wales Institute of Science, Technology and Advanced Studies, Chennai. Today, my title is Hyperbolic Iterated Function System. Hyperbolic Iterated Function System in Light Waves Images using Graph Theory. Abstract. Information about space and time is transmitted by light. According to quantum theory, light can act both like a wave and like a particle at the same time. The domains of optics, optical communications, and a variety of other related, both established and developing technologies are all founded on this feature. Lasers, holography, and fiber optic telecommunication networks are a few examples of technological innovations based on the manipulation of light. A new technique that enables the collection of more detailed visual data from our environment is the light field imaging. This paper describes a mathematical modeling to hyperbolic iterated function systems in light field images using graph theoretical concepts. Here we are going to see about light field images, graphs, and fractals. From this, it can be defined here, hyperbolic iterated function system for light waves images. Light wave images. The light field image, generally referred to as the holographic image, comprises the data on both spiral direction of light beams as well as their intensity in a stream. Even among experts in the imaging sector, light field technology, known as integral imaging, is a new idea for imaging whose benefits are not well recognized. Light field image will be used in a broad variety of applications in the future since it provides a wealth of optical and mathematical data. Graph theory is the study of graphs and its properties. It relates points and lines of the graph. A graph is defined as the set B, E, with B a finite non-empty set of vertices, E and a finite set of edges. Graph theory is one of the most modern branches of modern mathematics and computer applications. The last 3 decades have witnessed the spectacular growth of graph theory due to its wide applications in computer science, discrete optimization problems, combinatorial problems, and classical algebraic problems. It has a very wide range of applications in many fields like engineering, physical, social, and biological sciences. The theory of domination has been the nucleus of research activity in graph theory in recent times. Next, fractals. Fractals is a type of mathematical shape that are infinitely complex and self-similar. Fractals are distinct from the simple figures of classical or Euclidean geometry like square, circle, sphere, and etc. In the 17th century, philosopher and mathematician Gottfried Leibniz's works set the foundation for the early development of fractal geometry. The fractal dimension can be demonstrated with a specific example, Von Koch's snowflake curve from 1904. In mathematics, a fractal is any of a group of complex geometric structures with the fractal dimensions, a notion coined by mathematician Felix Hausdorff in 1980. Bernard Mendelfort created the term fractal, which is derived from the Latin word fractals in 1975. Mendelfort defined the new field of fractal geometry as a result of his inquiry into an obscure area of mathematics. A fractal is generally a rough or fragmented geometric shape that can be split into parts, each of which is a reduced size copy of the whole. This property is called a self-similarity. A mathematical fractal is based on regression. It has some features. It has a fine structure with arbitrarily small scales. It is too irregular to be easily described in traditional Euclidean geometric language. It is self-similar. It has a simple and regressive definition. They are mathematical sets with a high degree of geometrical complexity that can model many natural phenomena. Iterated function system is a simple mathematical tool for constructing fractal sets through a series of contractive affine applications. The iterated function system also serves as a basis for some data compression methods, especially images, since they allow obtain good approximation of objects of the real world. Hausdorff metric, that is the greatest of all the distance from a point in one set to the closest point in the other set. Underlying geometry of images. Visual light images are considered as the boundary lines of the structure clarity in the given images. Here the boundary lines in the visual light images taking a graph df as a set in the plane, and each curve, say dfi, where I belongs to plus infinity to minus infinity, is a subset of the line R. If x belongs to df, for every epsilon is greater than 0, in the interval x minus epsilon comma x plus epsilon contains the points of df in addition to x. Borderline fractals is described by a curve that undergoes in the iterated process. Consider a sequence of positive numbers wk with w not equal to 1. Here wk is greater than wk plus 1 up to wk by 2. Here the limit k tends to infinity, we get 0. The first set is a line segment df1 with length w not equal to 1. If the polygon dfk has been constructed consisting of many line segments by 2 segments of length wk plus 1. In the concept of fractals, contractions are very important. Finding contractions, they are not significant similarities, it's difficult. They affine transformations assets in changing the images designed by retaining the symmetry of the lines but not their lengths and angles. It is a method that designers can apply for image processing in machine learning algorithms. Furthermore, it is utilized to fix chromatic aberrations and bending moments brought on by the less camera angles. Because of contraction mappings, the point sets they are produced when they are applied to the segment of an image are less than the original size of that portion of the picture. The contraction mapping concept is regarded as the one of the most effective method to analyze nonlinear equations, including algebraic, integral, and differential equations. A fixed point theorem known as the mapping principle provides that a contraction mapping of the complete metric space has a unique fixed point. Light field images generate an image made up of a specific number of affine transformations, which provides a good approximation to the image of the attractor. It can be obtained that a metric space is df comma d, where df is a non-empty set and the metric is the function d from df into df tends to r is a real valued function with metric properties. When the objects can be approximated by attractors of an iterated function system and give to contractions that lead to a good representation of the given object. The objects in the visual light images can be bounded by fractal curves. These sets can be extended to provide a colored images by assigning a probability pi to each of the contractions di, where probability pi lies between 0 to 1 and the summation of all probabilities equal to 1. Without loss of generality, define a mass distribution mu on the attractor F such that mu of A equal to summation Pi mu of di power minus 1 of A. So here we define a definition hyperbolic iterated function system for light wave images. That is, first we consider the complete metric space df. Let df comma d be a complete metric space. Let f1 comma f2 comma f3 comma up to fn be a finite sequence of strictly contractive transformations fn from df to df for n equal to 1 comma 2 comma up to n. Then df such that f1 comma f2 comma up to fn is called the hyperbolic
2 minutes
iterated
left.
function system. Conclusion: this paper initiates the visual image field, constructs the fractal structure using contraction mapping. Iterated function system on cross product of Hausdorff space are attracted by superfractals. The future work will focus on developing super iterated function systems and the superfractals for some complicated images in light image fields. These are my references. Thank you.
Thank you, Ms. Razi. Any question from the audience? Okay, if not, let's thank the speaker. And with that, we pass on to the next talk of this session. The title of the talk is Radio Number and Antipodal Number of Spider Graphs. And the presenter is Mossadegh Hussain. So I would like to ask him to present his scheme and start.
Good afternoon, sir. Am I audible, sir?
Yes, you can start.
Good afternoon, sir. Myself, Mossadegh Hussain, Research Scholar, Department of Mathematics, Raiganj University. Now I present my paper entitled by Radio Number and Antipodal Number of Spider Graph. These are the outlines, abstract, introduction, and radio number and antipodal number of spider graph, and then references. A radio K labeling problem was introduced by Chartrand and investigated by Liu for a simple connected graph G equal to Vg, Eg and a positive integer K with 1 less or equal to K less or equal to diameter of G. A radio K labeling of G is a mapping F such that V of G to 0, 1, 2, dot such that mod of Fu minus Fv greater equal to K plus 1 minus D of U, V, where diam of G and dg of U, V denoted the diameter of G and the distance between U and V respectively. From the above definitions of radio K labeling of graphs, two radio stations which are at distance K plus 1 or more may get same labeling, that is the interference level has been considered up to K distances. A type of graph labeling that uses radio waves is the labeling of simple connected graphs. The most common graph labeled with vertex coloring is the graph G because the vertices are colored differently so that adjacent vertices do not get the same color. A K coloring of a graph G is a coloring that uses K colors. Chromatic number can be defined as the minimum value of K for which G exhibits the coloring. The problem of channel assignment was first put in the graph theory context by Hell. Graph theory described vertices of a simple connected graph as locations of radio transmitters or radio stations with vertices, labels corresponding to the assigned channels or frequencies. A graph which has one vertex of degree at least 3 and all other vertex are of degree at most 2 is called spider graph. In these presentations, we shall discuss the radio number and antipodal number of a spider graph of height h and t branches. Definitions. 1. A graph G consists of a pair Vg, Eg, where Vg is the non-empty vertex set and Eg is the set of unordered pair of distinct elements of Vg. The elements of Eg are called edges of the graph G. any two vertices u, v associated with an edge E are called end vertices of E. Definition 2. For a simple connected graph G with diameter q and positive integer k with 1 less or equal to k less or equal to q, a radio k labeling is an assignment f of non-negative integers to the vertices of G such that for any two distinct vertices u and v, let F be a radio k labeling of a simple connected graph G. The span of a radio k labeling F, denoted by span f of G, is the largest integer assigned to a vertex of G. That is, span f of G is equal to maximum of Fu such that U belongs to Vg. And definition 4, the radio k chromatic number of G denoted by RCK of G, the minimum span of all possible of radio k labeling of G. A radio k labeling F is called minimal if span F of G is equal to RNG. Here we draw two figure, that is the we take two path of four vertices and we give the labeling. First one, the highest coloring value is 9 and second one is the 5. So this is the optimal coloring is the second one. Different kind of labeling. For some specific values of K, there are specific names for radio K labeling as well as radio K chromatic number. If we take K equal to 1, then the labeling name is vertex coloring and called the chromatic number, that is chi of G. If we take K equal to diameter of G, name of the labeling is radio labeling and the radio number RNG. Similarly, if we take K equal to diameter of G minus 1, then name of the labeling is antipodal labeling and the called the antipodal number, that is AC of G. Now the theorem 1. Let G be a spider graph. Let G have T number of branches, namely P0, P1, P2 up to Pt minus 1, all of which are at a distance h from the centroid S of G. We denote this spider as STH, a vertex from ith branch and of height j of Vg minus singleton S is denoted by Vij. Then the following results are what? That is, cardinality of vertex set of Vst is equal to Th plus 1 and weight of STH equal to half into TH into H plus 1 and union of I equal to 0 to T minus 1 Pi is equal to STH minus singleton S. This is the vertex arrangement rules and we rename the vertices Vij by UL by the following rules and also let U0 equal to V0 the root vertex. In this way we get an increasing sequence U0, U1, U2 up to UN. This is the algorithm by which we get the result. Theorem 1. Let G be a spider graph and let G have T number of branches, namely P0, P1 up to Pt minus 1, all of which are at distance h from the centroid S of G. We denote this spider STH and from a vertex ith branch of height j denoted by Vij, the radio number of G RNG is equal to n minus 1 into q plus 1 minus Th into H plus 1 plus 1. Here n is the number of vertices and q is the diameter and T is the number of branches and H is the height of a branch. Here we take two figure. First figure, there are 7 T equal to, we take T equal to 7 and H equal to 3 and we find the radio number as similar for an odd case and for the second figure we take T equal to 8 and H equal to 4 and we find the radio number of the spider graph. And theorem 2, in similar way we can also find the antipodal number of an spider graph. That is, here also we take T equal to first in the first figure we take T equal to 7 and H equal to 3 and in the second figure for the even case T equal to 8 and H equal to 4. So these two figures from first theorem, that is theorem 1 is the a radio number of an spider graph and the result is this, and the second one is the antipodal number of an spider graph. So these are the references and then thank you. Hello sir.
Yes. Thank you. Any question from the audience? Anyone? Any question? Okay, then let's thank the speaker once again.
Okay,
And
thank you,
with
sir.
that, we move to the next talk. The title of the next talk is Some Variation of the Square Element Graph over a Group. And the speaker is Shomen Pradhan. So Shomen, can you present your screen?
Yes, sir. Yes. Sir, am I audible and visible? Audible?
Yes, 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 yes. Please.
Good afternoon, everyone. Myself, Mr. Soumen Pradhan, Assistant Professor, Department of Mathematics, Nagar College, West Bengal. Today, I am going to present my paper titled as Some Variation of Square Element Graph over a Group. And this is joint work Professor Sukhendukar, Department of Mathematics, Jadavpur University, and Dr. Bijan Biswas, Department of Science and Humanities, Ranaghat Government Polytechnic College. First of all, we give some introduction about this paper. Nowadays, the algebraic graph theory plays very interesting role to study of graphs in connection with many branches of mathematics. The interrelation between the algebraic structure and the graph theoretic structure has brought out many interesting results from the perspective of both algebra and graph theory. The square element graph, defined over a finite commutative ring by Sengupta and Sen, is perhaps the first instance where the set of squares of an algebraic structure is directly used for defining a graph. Later, Sengupta and Sen generalized the square element graph by defining it over any ring. After that, Biswas studied square element graph over some special class of rings. Later, they introduced the square element graph SQS over a semigroup S and studied some of its properties. Now we introduce square element graph over a group. The square element graph over a group was defined as follows. Let H be a group and consider G be a graph with V as a vertex set and E as a edge set. And here we take H is a vertex set. The set of all elements of H take the vertex set. Then any two elements AB belongs to V are adjacent to each other if and only if either AB or BA belongs to the set T square such that T belongs to H minus E set where E is the identity of the group H. And this simple undirected graph denoted by SQH and is called the square element graph over the group H. Now we introduce order 2 element graph over a group. Here I add some extra conditions with the square element graph over a group and get the order 2 element graph. Now the order 2 element graph over a group was defined as follows. Let G be a group, then the order 2 element graph of G is the simple undirected graph whose vertex set consists of all elements of G and two distinct vertices U and V are adjacent if and only if either UV or VU belongs to T square such that T belongs to G union A belongs to G such that A square equals to identity minus identity set, where is the identity element of G and it is denoted by S to G. And in this paper we use SG as a set of all squares of G and G2 the order 2 elements of G. Now from the given example, if we take G as the group G equals to Z6, then it is clearly said that SQZ6 is not connected, whereas S2Z6 is connected. And the next example shows that if we take the graph G, the group G equals to
হ্যালো,
yes,
ইয়েস কমপ্লিট করে দিছি, হলো শেষ। তুমি কোথায়?
G equals to Z4, then the graph S2 of Z4 is not connected. So from these two examples, it is clear that the graph S2G is not connected for some finite commutative group G. And from these two examples, we move to the next section, connectedness of S2G for some finite commutative groups. In this section, we mainly characterize those finite commutative group G such that the graph S2G is connected. As a result, if we take the group G equals to Z2 times Z2 times this is n copies of Z2, then the graph S2 of G is complete because a order of every element is 2. And take another result, if we take S be a non-empty set and take G be a group with power set of S and operation being symmetric difference, then the graph S to G is complete because order of every element is also 2. Here is a proposition: let G be a finite commutative group. If the graph S to G over a group G is connected, then S2 of Z2 cross G also connected. And next proposition, let G be a finite commutative group and the graph S to G over G is connected, then S2 of Z2 into 2n plus 1 cross G is also connected for any positive integer n. The next proposition states that if G is finite commutative group and S to G is connected, but S2 of Z4n cross G is not connected for any positive integer n. And the next proposition states that the finite commutative group G and the graph S to G is connected, then S2 of Zm cross G is connected where M is of the form 4n plus 1 or 4m plus 3. And the graph next proposition states that the graph S2 of Z4m cross Z4n is not connected for any integer m and n. And the next proposition is that states that the graph for finite commutative group G, the graph S to G is connected if and only if G is isomorphic to ZR1 times ZR2 times ZRK, where Ri belongs to X belongs to Z, such that X is of the form 4n plus 1 or 4n plus 2 or 4n plus 3. Here is an important theorem: the graph S to Zn is connected if n or n by 2 is odd number, whereas the graph S to Zn is disconnected if n by 2 is an even number. And next theorem says that the graph structure of S to Zn is complement graph of k1 plus n minus 1 by 2 into k2 when n is odd number, and complement graph of 2k1 plus n by 4 minus 1 into k2 plus complement graph of n by 4 into k2 when n by 2 is even number, where k1 is a complement graph of 1 vertex and k2 is a complement graph of 2 vertex. And the next section is connectedness of S to G, where G is finite non-commutative group. For any integer n, the graph S to Sn is connected, and for any integer n, the graph S to Dn is connected. And not only that, the graph structure of S to Dn isomorphic to complement graph of n plus 1 k1 plus n minus 1 by 2 k2 for any odd integer n. And here is an important proposition: let G be a group, Sg be the set of square of G and G to be the set of those elements of G whose order is 2 but not in Sg. Then in the graph S to G we have degree of any vertex x equals to cardinality of Sg union Gt minus 1 when x square equals to identity, and cardinality of Sg union Gt minus 2 otherwise. And next section we have the order 2 element graph of finite groups up to order 16. In this section we characterize the connectedness of S to G, where G is the group of small order up to 16. Here is the table. First column denotes the order of the group as well as order of the vertex of the graph, and next column denotes the graph group structure of the small order group, and third column describes the graph structure of S to G, and fourth one the connectedness and planarity structure of the corresponding graphs. These are the references which are used to prepare my paper, and last stop. Thank you.
Thank you, Showman, for this nice lecture. Any question from the audience? Okay, I have one question for you, Showman.
Yes.
That you have defined a graph over a group. Now, the question is that suppose I am giving you a graph, can you identify the group from that graph? And from which type of group is it coming? The opposite question, actually.
No, I have no idea.
Okay. Thank you.
Okay.
So let's thank the speaker once again. And then there is a slight change in the schedule. The next speaker is not present right now. I mean, she will not be delivering it now. So we pass on to the next topic. So the title of the lecture is Some Properties of Two Torsion, Two Singular Graph of Modules, and the speaker is Shongita Datta. Is she here? Shongita Datta?
Yes.
Okay,
Yes.
you can present your screen.
Okay. Is my screen visible?
Yeah, it's coming. Yes. Yes.
So I'm Dr. Sangeeta Datta from Department of Mathematics, Northeastern Hill University. Title of my presentation is Some Properties of Two Torsion and Two Singular Graphs of Modules. In 2011, Atani and Habibi introduced the total torsion element graph in R module M, denoted by T lambda M, in which any two distinct elements M and N in M are adjacent if and only if M plus N belong to Tm, where Tm is the set of all torsion elements of the module M, that is set of all M in M such that Rm is 0 for some R in R. In 2015, Goswami and others introduced the total graph of a R module M with respect to singular submodule Zm, denoted by T gamma M, as an undirected graph with vertex set as M and any two distinct vertices X and Y are adjacent if and only X plus Y belong to Zm, where Zm is the set of all X in M such that Xi is 0 for some essential ideal I of R. So in this paper, we define two graphs of an R module M called the two singular graph with respect to singular submodule Zm of an R module M, and the two torsion graph of M over R with respect to the set of torsion elements of M. We find various graph parameters of this graph and characterize modules in terms of these graphs. So graph theory finds its application in a number of branches of mathematics. In recent years, graph theory has emerged as one of the important tools to characterize algebraic objects. Way back in 1955, Brouwer and Fowler introduced the idea of associating graphs to the algebraic structure group in order to classify finite simple groups. Then in 1988, IIIB started things by associating to it a graph termed zero divisor graph. Followed by Beck, many mathematicians derived interesting characterization of algebraic objects such as rings, modules, and vector spaces. The total graph of rings was introduced by Anderson and Badawi in 2008. This graph has taken the attention of many mathematicians in the last few years, and many interesting properties of this graph was derived. Subsequently, in 2011, Atani Habibi considered the total torsion element graph of an R module M. Goswami and others in 2015 defined the total graph of an R module M with respect to singular submodule Zm. The double total graph of a ring R was introduced by Datta and Sangeeta in the year 2018, and this graph was found to characterize the fusible rings and the weakly fusible rings. And these two graphs mentioned in the paper, this presentation, are based on this double total graph of a ring. So a graph is a pair of pair BG-EG, where BG is the set of elements called vertices and EG is the set of elements called edges with a relation that associates with each edge two vertices called its endpoints. The sequence of edges x0, x1, x1, x2, xk minus 1, xk in a graph is called a path of length k. A path between x and y is called a cycle if x is equal to y. We say that G is connected if there is a path between any two distinct vertices of G. If vertices U and V are connected in G, the distance between U and V in G, denoted by DUV, is the length of the shortest UV path in G. The diameter of G, denoted by diameter G, is the maximum distance between two vertices in G. The girth of G is the length of the shortest cycle in G, and it is denoted by GRG. A bipartite graph is one whose vertices can partition into two subsets x and y so that each edge has one end in x and the other in y. A complete bipartite graph is a simple bipartite graph with bipartition xy in which each vertex of x is joined to each vertex of y. For a graph G, the degree of a vertex B in G denoted by degree B is the number of edges incident to B. A set of vertices of a graph G is independent if the number of if the vertices are pairwise non-adjacent. The independence number of a graph G alpha G is the cardinality of the largest independent set of G. A subset of vertex set is called a clique if every pair of vertices are adjacent. Then the clique number omega G is the cardinality of the largest clique in a graph. An Eulerian two-row circuit in a graph is a closed walk including all edges of the graph. A graph G is said to be Eulerian if it has an Eulerian two-row circuit. A Hamiltonian cycle in a graph is a cycle including all the vertices of the graph. A graph is Hamiltonian if it has a Hamiltonian cycle. The definition, the two singular graph of a module M with respect to singular submodule Zm of M is an undirected graph with a vertex set M and any two distinct elements x and y in M are adjacent if and only if u plus x plus y belong to Zm for some u in Um where Um is M minus Zm, and this graph is denoted by Tu gamma M. The two torsion graph of M over R with respect to the set of torsion elements of M is denoted by Tb lambda M and defined as the graph with vertex set M and any two distinct elements x and y in M are adjacent if and only if B plus x plus u belong to Tm for some B in Bm which is M minus Tm. If Zm is equal to M, then we have Tm is equal to M, and in this case the graphs are isomorphic and isomorphic to complete cardinality M. So we consider only here UM non-empty and Bm in case of Tu gamma M and Bm non-empty in case of Tb gamma M. So some properties or remarks regarding Tu gamma M that Zm is a submodule of M, but Tm, first of all, regarding module, Zm is a submodule of M always, but Tm need not be a submodule of M. For example, in the module G6 or G6, Tm containing the elements 0, 2, 3, 4 are the torsion elements, but we know that Tm is not a submodule because 2 plus 3 does not belong there. Therefore, so next we see that Zm is a subset of Tm, and so Vm is also a subset of Um. The total torsion element graph of a module T lambda M is a subgraph of the total graph with respect to singular submodule T gamma M. This is an observation. If Zm is equal to Tm, then Tu gamma M is isomorphic to Tb lambda M. And it is clear that if Z belong to Zm, then minus Zm, Z also belong to Zm, and U belong to Um implies minus U belong to Um. If Z belong to Zm and U belong to Um, then it is easy to see that Z plus U belong to Um. If Um is empty, then Tu gamma M is equal to T of gamma M. And if Bm is empty, then Tu lambda M is equal to T lambda M. If the cardinality of Zm is K, where K is greater or equal to 2, then cardinality of Um is greater or equal to K. So some results, proposition.
You have 2 minutes left.
Total graph T gamma M is complete graph if and only if Zm is M. Tu gamma M is connected and diameter Tu gamma M is less than or equal to 2. If cardinality Zm is greater or equal to 2 and cardinality Um greater or equal to 2, then girth is 3 or 4. If cardinality is greater or equal to 2, then independence number is greater or equal to Zm, otherwise it is 1. We observe that if x and y are two distinct elements of M and cardinality M is bigger or equal to 1, and then if x plus y belong to Zm, then x and y are adjacent, not adjacent, whereas if x plus y belong to Um, then x and y are adjacent. Next proposition we have, if Zm is 0, then alpha Tu gamma M is 1 if and only if x belong to M imply that 2x belong to 0. And coordinate GM, if suppose coordinate GM equal to 3, then independence number is 4. If independence number is 4, with an independent set x1, x2, x3, x4, then 2x1 equal to 2x2 equal to 2x3 equal to 2x4. If let coordinate Zm equal to k, where k is not equal to 1 or 4, then independence number is of this graph is k. If coordinate Zm is greater or equal to 2 and coordinate Zm is um is greater or equal to 2, then the domination number gamma tu gamma m is 2. And it is easy to see that if either Zm is 0 and coordinate um is 1, then domination number is gamma tu gamma m is equal to 1. If um is non-empty, then degree of a vertex tu gamma m is either coordinate um or coordinate minus 1 or coordinate minus 2. Tu gamma m is an Eulerian graph if and only if no element of um is additive inverse of any element of um. Tu gamma m is isomorphic to the complement graph of total graph of with respect to torsion element. Then here we have certain characterization regarding Hamiltonian graph of Tu gamma m depending on the minimum degree of the vertex. And Tu gamma m is a regular graph if and only if minimum degree is equal to coordinate um. If coordinate gm is not equal to 1, then clique number is given by of this graph is given by coordinate um by 2 plus 1 if and only if no element except 0 of m possesses self-additive inverse. Let x and y belong to um, then x is adjacent to y if and only if every element of x plus zm is adjacent to every element of y plus zm. Next, we come to some properties of TV lambda m. TV lambda m is a connected graph. Tm is, if Tm is a submodule of M, then Tm is independent set in TV lambda m. And it is clear that Tu gamma r is isomorphic to TV lambda r as Tr is equal to Zr. If coordinate Tm is greater or equal to 2 and coordinate Bm is greater or equal to 2, then GART is 3 or 4. If coordinate Bm is bigger or equal to 1, then independence number is given by bigger or equal to coordinate Tm, otherwise it is 1. If Tm is 0, then independence number is 1 if and only if x belong to M implied 2x equal to 0. Coordinate Tm equal to 3, and if alpha Tb is Tb lambda m is 4 with an independent set x1, x2, x3, x4, then 2x1 equal to 2x2 equal to 2x3 equal to 2x4. If coordinate Tm is k, where k is not equal to 1 or 4, then alpha Tb lambda m is equal to 4. Let Tm be a submodule of M. If coordinate T of M by Tm is 2, then Tb lambda m is isomorphic to the complete bipartite graph on with bipartite set coordinate Bm and Tm. Let 2 belong to Zr. If Tb lambda m is isomorphic to the complete bipartite graph, then coordinate of M by Tm is equal to 2. Let 2 does not belong to Zr, then Tb lambda m is isomorphic to the complete bipartite graph if and only if Tm is equal to 1. Let M and N be two elements of Tm, then the following statements hold that if 2 belong to Zr, then M plus Tm is an independent set in Tb lambda m. If 2 does not belong to Zr, then M plus Tm is a clique in Tb lambda m. No element of the n plus Tm is adjacent to any element of m plus Tm if and only if n plus m belong to Tm, and this is the characterization of the graph Tb lambda m. Let Tm equal to coordinate Tm equal to alpha and coordinate m by Tm equal to beta, then the following statements are true that if 2 belong to Zr, then the graph Tb lambda m is isomorphic to it's isomorphic to complete graph on beta minus 1 times on coordinate alpha. And if 2 does not belong to Zr, then Tb lambda m is isomorphic to complement of the disjoint union of beta minus 1 by 2 times k alpha alpha. So these are a few results which we have derived, and so these are my references. Thank you.
Thank you, Dr. Sangeeta. So with that, we pass on to the next talk. The title of the next talk is Behavior of Total Variation under a definite chaotic map on the real line or on a graph. And the speaker for this talk is Mr. Shubhamay Mondal. Shubhamay, can you please present your screen?
Okay, just a minute. Is my screen is visible?
Yes, yes, you can start.
Okay. Hello everyone. Myself Subhamoy Mondal, research scholar at Presidency University. Today, the topic of my presentation is the following. The title being Behavior of Total Variation under a Devani chaotic map on the real line or on a graph. So a dynamical system means a pair X and F, where X is some topological space and F is a self map with some additional structure such as measure theoretic or topological. Now, throughout today's talk, I will be take X as a metric space and F is just a continuous self map. Now, there are so many ways to study the dynamical system. One of the questions that may capture the chaotic nature of the underlying self map is to look at how the variation of a typical curve in that space, that is X, evolves under the iteration of the map F. Now, our motivation comes from the following two results. One is due to Mitsurugi and Zling. They told that if we have a continuous interval map on a compact set 0, 1 say, and which is continuous and piecewise monotone, then topological entropy of the system is actually equal to the exponential growth rate of the variation of Fn. And topological entropy means that it is actually the measure of the exponential growth rate of the number of distinguishable orbit of this system, which is actually a non-negative quantity and maybe infinite. Second one is due to Chen Huang, which says that if F is a continuous interval map and it has sensitive dependence on initial condition. Now, if Devani chaotic map has that property, then this quantity, that is variation of Fn on any subinterval, tends to infinity. Now, to move forward, we need some definitions. First of all, I think we all know what is actually the total variation and total variation of a curve. So next is a map is called Devani chaotic if it is topologically transitive and the periodic points of F are dense in X. That is, periodic points means if we take any point X in that space and start to iterate it, then when at the first time we come back to X itself, then it is called the periodic point of this space. Third one is F has sensitive dependence on initial conditions. Now, a system is called topologically transitive if we take any two non-empty open set U and V and start to iterate it at some finite iteration, you will fall into the open set V. And if in particular F2 is transitive, then it is called bitransitive. And if Fn is transitive for all n, then we call it totally transitive. Now, mixing is another important property of the dynamical system, which is actually the generalization of topological transitivity. This says that the intersection actually holds after some finite times. Now, in our case, as X is an infinite metric space, so in the condition of Devani's definition of chaoticity, 1 and 2, that is topological transitivity and density of periodic point, force the sensitive dependence on initial conditions. Now, the concept of horseshoe is actually an important concept in our case. Now, a horseshoe, an S horseshoe for a real valued continuous map means we can have S closed interval with pairwise disjoint interior such that the image of each Ji actually contain the union of JIs. Now, this is an example of a topological transitive map, and one thing to be noted that the slope of this map is actually greater than 1, and this will help us that F being totally transitivity. Now, totally transitivity in that case is actually force that F is Devani chaotic, because due to the result of JS Canovas, which tells that if we have a continuous real value transitive map, then the periodic points are dense, that is F is Devani chaotic, and the four conditions are equivalent, that is if F is bitransitive, then it is automatically totally transitive and mixing. And the fourth one is if we take any positive number and consider the symmetric interval minus m comma n, and if we take any interval j, and then after some stage of iteration of j, this will contain minus m comma m. And third one is that if f is just transitive but not bitransitive, then f has only one fixed point a, such that f cyclically permute a infinity and minus infinity a, and the f2 over a infinity and minus infinity a is actually bitransitive, and this will imply totally transitivity. Now we state our first result, that if we have a non-constant curve in the real line, and if we have a transitive real valued map, then this, that is variation of fn composed gamma, is actually tends to infinity, and moreover the exponential growth rate of the variation is strictly positive. Due to lack of time, I just keep the proof of this theorem. To prove this theorem, we just need some lemma and a proposition. The first lemma tells that if we have, if the first lemma eventually tells that the variation goes exponentially along the iterates that are multiple of some positive integer p, and this will actually follow from the condition of the theorem that f has an t horseshoe, so f to the power p has t to the power p horseshoe, and we get the result. The proposition actually tells that we can actually fill in the gaps that conclude that the variation grows exponentially along the iterates of any sequence. That is the generalization of this lemma. And now the idea of this theorem, that we use the result of JS Canovas, that is a topologically transitive map, either it is totally transitive or it is bitransitive. If first one, if it is totally transitive, then at some multiple of m under a periodicity point, that is some pm, it actually contains a horseshoe in the image of the graph. And if f is transitive but not bitransitive, then the same things will happen, but the iteration may not be the same. So using the above proposition and lemma, we can conclude our theorem. The next is the total variation of iterates of a chaotic map on a graph G. For this, we need the notion of a graph. Actually, a graph, a topological graph is actually compact connected house of space, which is a finite union of homeomorphic copies of a compact interval 0, 1, such that they can intersect at most at one point, right? And an interval of a graph is actually a homeomorphic to one of these intervals 0, 1 or close 0 closure and elsewhere other, and that is an interval of a graph which is entirely lies in an edge of a graph. Now this theorem tells that if gamma is a non-constant curve in G, such that f from G to G is Devani chaotic, then variation of fn composed gamma tends to infinity, and the same thing, that is the exponential growth rate of the total variation, is strictly positive. Now f is Devani chaotic. Now we need that the topological entropy must be positive. As f is Devani chaotic, then by result of Miserovic, that Devani chaotic means that it has topological entropy positive, and by result of Miyazawa, we can have that under some iterates, we can have the under some iterates fm has some horseshoe, right? This is the result of Miyazawa, and this is the result of Miserovic. Now our basic argument actually depend on the following proposition, that if we have a Devani chaotic graph map and gamma is a non-constant curve which lies entirely in an edge, then we have some positive integers n naught l and a closed interval k, such that the iteration of gamma 0, 1 under n naught, which actually consume whole k, and fl actually has an s horseshoe in the image of this graph. And to prove this proposition, we have broken it up into in few elementary lemmas so that it is easier to handle. Now this lemma actually tells that if we have a horseshoe J1, J2, Js, and I is a non-degenerate interval, and if we have a map gamma from this sequence space to this sequence space such that gamma of J1, J2, Jn is equal to J1, J2, Jn, that is we just delete the last component, then G to the power n has S to the power n horseshoe. The second lemma tells that if alpha is an infinite sequence of symbol and alpha to the power n is just J1, J2, Jn, and J to the power alpha n is defined recursively from the above lemma, then the whole intersection is non-empty. And if we take any two disjoint symbols, then the intersection of J alpha and J beta is empty. Third one is that the intersection of J alpha to the power n for n equal to 1 to infinity is a closed interval, maybe degenerate or a non-degenerate, that is singleton. And for the last one is there are at most countably many points such that J alpha is non-degenerate. Now the other lemma says that if J alpha is precisely the subcollection of disjoint of degenerate intervals, and X alpha is equal to J alpha, and which is lies in the interior of J, then there exists some positive integer n such that J of alpha to the power n is contained in interior of J for after some certain stage. Now transitivity is actually not enough in determining if a certain point goes inside some forward iterates of an open set. So we need the spectral decomposition due to block to determine that only countably many points are such that they don't go inside any forward iterates of some open set. These are actually called the inaccessible points, and the result by Haran-Jig that there are only finitely many points in a mixing graph map which is actually inaccessible. And this is the result of block decomposition. That is, block decomposition says that if F is a Devani chaotic graph map, then either it is mixing or G can be partitioned into finite number of subgraphs such that their intersection contains at most finite number of points, and this partition cyclically permute by F, and after some iteration if we restrict F on these subgraphs, then they are all mixing, right? This theorem says that there are uncountably many points which can be accessible. Now the following the following proposition is actually essential adaptation from the real line case to the topological graph. That is, if gamma 0 is a curve which lies entirely in an edge of a graph, and F is a Devani chaotic map, and if we assume that an S horseshoe lies within the image of the graph under some iterate, then this condition is hold. So all the previous ingredients now come together to give the above results, and that's all. These are the references. Thank you.
Thank you, Shubhamoy. Any questions from the audience? If not, let's thank the speaker once more. And with that, we pass on to the next talk. The title of the next talk is Universality of L21 Coloring of Graphs. And the speaker will be Dr. Ushnish Sarkar. Ushnish, can you hear me?
Yes, Pogramanda, thank you.
Yes, please.
I am sharing the screen now. Is my presentation visible?
Yes. You can start. You can make it full screen.
Yeah.
Yes,
Okay.
it's fine.
Okay. Hello, everybody. Good afternoon. I am Dr. Ushnish Sarkar. I am Assistant Professor of Mathematics in Netaji Subhash Open University. Today, the title of my talk is Universality of L21 Coloring of Graphs. Now, before we go into the main issue, let's see some things like what is a graph coloring problem. So it is basically assigning some non-negative integers, which we will say color, to the vertices of a graph G, such that no two adjacent vertices receive the same color. It's kind of assigning colors to the, say, political map of the West Bengal, where we are assigning different colors to different districts in such a manner that no two adjacent districts should receive the same color. Now, the minimum number of integers with which this assignment can be done, the minimum number of colors we spent here, is termed as the chromatic number of the graph, and it is defined, it is denoted by chi of G. Now, another salient feature of this general graph coloring problem is that no integer between the maximum integer or maximum color used and the minimum color used is left unused here. So suppose I am starting from a minimum color 0 and I end at the maximum color 5, then for an optimal coloring, all the colors in between, so 0, 1, 2, 3, 4, and 5, all the colors should be used. So here's an example of general graph coloring problem. So as we can see that this graph is colored with just two distinct colors, 0 and 1, or I can also say this 1 and 2, and here the chromatic number is 2. Now we shall talk about the frequency assignment problem, which is abbreviated as FAP. Now, as it is evident from the name itself, it is the task of assigning frequencies to the transmitters, or better said transceivers, in a wireless sensor network. Now, these frequencies are treated here as non-negative integers. Now, it is not enough, or we are not at the free hand to assign frequencies as per our whims, because the frequencies or procuring frequencies is actually a very costly business. These are unavailable due to financial and other physical restrictions. Also, there is another challenge of interference. That is, suppose two closed or nearby transmitters or transceivers are relaying informations in a frequencies which are identical or very close to each other, then their transmission, each transmission of each transceiver or receiving of each transceiver will be disturbed by a phenomena called interference. So thus, in a nutshell, the factor of interference can be listed as distance between transmitters or transceivers, the geographical position of them, the power or the strength of the signals, the weather conditions as well, and assigned frequencies as well. Now, here's a pictorial description, an illustration of what we are actually dealing with. So as we can see, there are some antennas. Their region of transmission are intersecting, and at the right side of this slide, I have written co and co-adjacent channel interference, which is basically interference due to two nearby channels or not exactly nearby, but they are also very close in that sense. So the task in FAP or frequency assignment problem, we have actually two tasks. One is to minimize the cost or the cost effectiveness. That is to minimize the difference between the maximum and the minimum frequencies assigned. And simultaneously, we'll also have to perform another task, that is tackling the interference. That is, allotment of frequencies to be done in such a manner that the frequency difference of the transmitters increases with their increasing proximity or the nearness. So here is another diagrammatic or pictorial presentation of this problem, where in the top we are seeing a picture where the transmitters or transceivers, or we can take them as antennas, are distributed in a geographical region. And in the left, I have denoted these transceivers or the transmitters as some dots or vertices. Actually, these are dots here, and in the right hand side, we are taking them as vertices of a graph. And again, in the left, if the region of transmission of two transmitters, if they intersect, then we will put an edge between those two corresponding vertices. So thus, in the right, we are getting a graph theoretic model of the frequency assignment problem, or actually the distribution of the transmitters. Now, here the graph theoretic modeling of the frequency assignment problem, which I have also said, the transmitter locations of a network as considered as vertices. Edges are assigned between two transmitter locations if they can broadcast or receive the transmission of each other. And the third one is a crucial one, that as the frequencies are uniformly spaced in the spectrum, the frequency assignment of the networks are basically integer leveling. So we are ultimately seeing this problem as coloring a graph with non-negative integers, and of course keeping in mind the factor of interference. So here is a more technical, more formalities here. That is not. It's quite clear by now that not all the graph coloring satisfies the conditions of the frequency assignment problem. Now, there is a certain kind of graph coloring problem, say LP1, P2, PM coloring. And here, as we can see in the slide, the first point is this P1, P2, PM are a monotonically decreasing finite sequence. And if this sequence of length m, this means I don't have to bother regarding the interference after mth distance, after the distance m. First one. And second thing is that until the m distance, that is from 1 less or equals to I less or equals to m, the frequency difference of two vertices, as we can see in the third point, I have written this like absolute difference of f of u minus f of b, where f is the assignment, is at least pi, where I is the distance between u and b. Now, from this point, we are entering another crucial graph coloring scheme, that is radio K coloring problem, which is a particular variation of this LP1, P2, PM coloring problem. And here we are simply taking pi, as we can see in the first line of the slide of the main content, that for any k greater or equals to 1, pi is taken as k minus I plus 1. Now this turns the problem of LP1, P2, PM into the LK, k minus 1, k minus 2, dot dot, k minus m plus 1 coloring problem. So here the requirement of avoiding or keeping the absolute difference of the frequencies is gradually reducing by 1 as the difference grows. So, and here at the end, there is a formal definition, and the restriction is f of u minus f of b. Their absolute difference is greater or equal to k plus 1 minus distance of uv. Now, there are some few variations of this radio k coloring problem. For k equals to 2, this problem becomes L21 coloring, which we will talk today. And for k equals to 3, it becomes L31 coloring problem. For when the k is diameter minus 1, it is called antipodal coloring, and when it is exactly the diameter, it is called the radio coloring. Now, here are some examples of L21 coloring problem. As we can see that these are two examples of optimal radio coloring problem, where, sorry, optimal L21 coloring problem. But the first one uses every color in between from 0 to 5, whereas here in the second one 4 is not used. Now, as you can remember, I have said this at the very beginning that this salient this existence of hole, that is unused color, cannot be seen in graph coloring problem in general. Now, here are some preliminary terms. The span is the minimum color used, and the difference between maximum color used and the minimum color used. Now, the minimum possible span here, we say them as we say this minimum of the span as lambda chromatic number or lambda number of the graph. And without loss of generality in the third point, we assume that the minimum color use is 0 here. Also, any optimal coloring, that is the color which span lambda to 1 of g or lambda g, is called a lambda coloring of g. Okay, and we have also seen what is the hole here. Any integer in between the minimum and maximum which is not used as a color is said to be a hole. Now, let's talk about some important constructions, as they are important in our discussion. Here, we are giving a recursive construction of a family of graphs. Okay. Let's talk about first G3. Actually, we are starting our recursion from n equals to 3. Now, here we are in G3, we are taking 4 vertices, V0, V1, V2, V3. And the edge set is actually from V0 to V2, I am assigning an edge. From V0 to V3, I am assigning an edge. From V1 and from V1 to V3, I'm again assigning an edge. Now, as you can see in the picture at the bottom, that from V0 to V1, there is no edge. Okay. And the edges are, as I have already said. Now, for the next step, or the next construction, say G4, G5, we are actually doing is that we are keeping the Gn minus 1 intact. Okay. And adding the nth vertex more. And then what I am doing, that I am adding the edges of the form Vi to Vn, where 0 less or equals to I less or equals to n minus 2. So actually, as you can, the essence of this construction is we are avoiding edges between two consecutive vertices. And it's very easy to compute that. It's quite obvious that GT has exactly t plus 1 vertices, and actually t choose 2 edges. Another important construction, here I am constructing a family GTL. Again, here t starts from 3, it's an integer, and we are actually taking t plus 1 number of mutually disjoint sets, each of size L. So that's why it is GTL. And the age distribution is here like this. In the first bullet, I can see that if X belongs to Vm, then there exists a unique Y belongs to Vp such that Xy is an edge. And here the M and P are regulated by the restriction that here 0 less or equals to M less or equals to P minus 2 less or equals to T minus 2. So essentially, I am keeping M and P at least 2 distance apart. And another important point is that if U and V belong to the same class, same vertex class, then we will not assign any edge in between them. Okay, and in that case, it is again very easy to compute that each such member of this the G of this the family GTL have exactly T plus 1 times L vertices and T choose 2 times L edges. Now, now I will show here some theorems, and for sake of brevity, I will be skipping the proofs. The first theorem here is for each n greater than 3, as I can see, the mapping. So I am assigning ith color to the VI for VGN, the first construction I have shown you. Now, this is the lambda coloring, and I can also show, it can also be proved that this is an optimal lambda coloring. So the lambda chromatic number of such Gn is n. So this Gn is our first construction. Now, regarding our second construction, the family GTL. Okay, here the first theorem is for positive integers t greater than 3, as I can see, and any positive integer L. I'm again assigning them color like M to VM. Okay, where VM belongs to that capital VM, that mth partition with 0 less equals to m less equals to t. This is a lambda coloring of each member of the graph. And interestingly, again, it can be shown that it's an optimal coloring, and so the lambda chromatic for each member of the graph is T. So here, there is a point to be noted that each member of GTL has lambda chromatic number T. Now our main result, which is regarding the universality. In what sense? That let's see the theorem. Here I am saying that suppose I am given a graph G with lambda chromatic number T, which at is 3, of course, and suppose C0, C1 up to Ct be the colored partition of the vertex set G. As we all know that the coloring gives a partition of the vertex set. So at this partition is with respect to an optimal lambda coloring C. Then there must exist a graph G star from that the family which we have already seen in the second construction, G star belongs to GTL, such that G is a subgraph of G star. And what is L? L is the maximum cardinality of the colored partitions. And here is the proof. The main technique of this proof is basically see here, each CIs or CMs are the colored partition, and if L is the maximum cardinality of the colored partition of the partitioning set, then I am plugging in suitable number of vertices to each CM, and that set I am naming them as YM. So such that size of CM plus size of YM is equals to L. Obviously, these YM and CM are mutually disjoint. Now I am identifying, I'm actually constructing a set ZMP here. What is ZMP? This is those vertices of VM such that U has no neighbor in VP. So here we can see that for each subsuitable M and P, that is where M and P are separated by at least distance 2, and for each X belongs to VM minus ZMP, there obviously exists exactly one vertex Y in VP minus ZPM. So here the order is reversed such that XY is an edge. And converse part is also that if U is an edge in G, then due to the fact that C is a lambda coloring, there exist integers M and P, again with the same condition that M and P are separated by at least distance 2, at difference 2. one of them, that is say U belongs to CP and B belongs to U belongs to CM and B belongs to CP, and hence we can conclude that V is the only neighbor of U in CP and vice versa. Now we are constructing a graph G, which is actually the universal graph, or the graph belonging to the universal family GTL, the G star, with the vertex at VM, and the edges of G are edges of G star. Also, there's an interesting fact that size of GMP and size of GPM are basically the same. And for each U belongs to ZMP, we associate a unique ZPM, a unique vertex V belongs to ZPM, and we are joining these two vertices with an edge. Okay, and thus we are getting a G star which is belongs to this universal family of graphs. Universal in that sense. So this was my main result, and these are few of my references. Thank you.
Thank you, Dr. Sharkar. Any question from the audience for him? Okay, if not, then let's thank the speaker once again. And now we pass on to the next talk. The title of the next talk is Metric Dimension of Cube of Trees, and the speaker is Dr. Sanchita Pal. So I would like to ask Sanchita to present her screen.
Thank you, Anshumanda. Am I audible and the screen is visible?
Yes, both.
Okay. Good afternoon, everyone. First of all, I would like to thank the organizers of this conference, MSAST, for giving me the opportunity to present. My name is Sanchita Pal. I'm an assistant professor of Department of Applied Mathematics, Dinobandhu Andrews Institute of Technology and Management. The title of my presentation is Metric Dimension of Cube of Trees. The concept of metric dimension was introduced by Slater, Harary, and Melter in 1975. Since then, it has been widely investigated for many graph classes. Metric dimension is a parameter that has various applications in graph theory, pharmaceutical chemistry, robot navigation, combinatorial optimization, sensor networks, and many more real-life problems. So, what is the definition? Now, given a connected graph, a subset of vertices W is called a resolving set if for any two distinct vertices UV, there is a vertex Wi such that distance from U to Wi is not equal to distance of V to Wi. Now, these vertices of W play an important role in uniquely identifying each pair of vertices by comparing their associated codes. Now, by code of a vertex, we mean a k-tuple, which actually every coordinate of it is distance of the vertex V from each of the vertices of W. Okay, so if any two vertex had different codes, that means, that vertex Wi resolves U and V. So now, any resolving set containing minimum number of vertices is called metric basis of G, and the number of vertices in a metric basis, that is the cardinality of the set, is called a metric dimension, and it is denoted by the symbol beta G. Now, this is a known result for a tree that if it is not a path and LV be the number of legs attached to any vertex V, then beta t is summation of LV minus of 1. Now let's look at this example for this clarification. So here you can see that if we take this vertex S1 say, so there are 3 legs are attached with it, right? So except one, from other two, we need to pick at least one vertex in the resolving set. So we have taken these red ones from these two. So from each of these major stems, S1, S2, S3, all of them, we have taken all except one vertices in the resolving set of it. So if you count them, the number is 10 here for this particular example. Now we move to the main topic of concern, that is cube of trees. So that is T cube. So in T cube, what we do, any two vertices are adjacent when their distance is at most 3. That means if you look at this figure, so I have joined every vertex which is adjacent to the center vertex V, which are at distance 1, 2, or 3 distance. So you can see that U is at 3 distance from V. So, but if you consider its distance in T cube, it will become 3 by 3. So that is 1. So 2 by 3, if it is at 2 distance, then also ceiling of 2 by 3, that will give you 1. So here is how the computation goes. Now, we find out that beta t cube is always greater than equal to beta t for any tree. And if S is a resolving set of T cube, then for any vertex X, S contains a vertex from each component of T minus X except one, with one exception. Now, next we move to the properties regarding resolvability in T cube. So, as you have already seen in the definition, that to resolve UV, now we need to get some vertex Wi from W, right? Now UV may be adjacent, may be non-adjacent, right? So first of all, we have considered when UV is an H in T cube. So obviously there will be some conditions. I mean, regarding dt of UV will be 1, 2, or 3. So better we move to this figure to clarify the idea. So first, in the first picture, dt of UV is 1. Now you can see, if we take any x which is left to you and is in 0 modulo 3 distance, that then we can consider dt of xu to be 3k, of the form 3k, right? That is k in t cube. I mean, but if we consider dt of xb, that will become 3k plus 1, which is k plus 1 in, if we compute in t cube. So that is different from k. So that's why x resolves uv. Now, similarly, when dt of uv is equal to 2, we see that x must be at 0 or 2 modulo 3 distance from u or v. And third figure is for when dt of uv equal to 3. Then we don't have put any restriction of the distance between x and u, if it is left to u or right to v. But if it is within the same component of u and v, then I mean, distance between u and x must be 0 modulo 3, or distance between x v must be 0 modulo 3. So these are the three conditions when uv are adjacent vertices. And when UV are two non-adjacent vertices, then also we find out some conditions. And using these two lemma, we able to find out the necessary and sufficient conditions for a vertex subset to become a resolving set for T cube. Now, this is the most important theorem of our article. Now, we only need to find out the conditions of UV when UV is less than equal to 5. I mean, for adjacency case, we have seen the distances 1, 2, and 3. For non-adjacency cases, we need to only look for the cases when dt of UV is 4 and when dt of UV is 5. So in these cases also, these positions of red vertices, as we already have described here, can only resolve this UV. Now, all these conditions are used along with the condition 1, that for every vertex V, S contains a vertex from each component of T minus V except 1, helps us to, I mean, get the sufficient condition for a vertex set to become a resolving set for T cube. Now, next we move to the lower bound of beta T cube, which is actually beta T plus summation of mi minus L, where L is the total number of major stems of T containing at least 2 mid legs, and mi is the number of mid legs attached to every major stem Vi, where mid leg is nothing but the leg which is of length 2. So here in case of V1, you can see that there are 2 mid legs are attached. So if you compute this, so beta t is nothing but 6, as we have computed for the last case. But this summation is nothing but 2 minus of 1. So that is 1. That's why it is 7. Okay, so the extra inserted vertex is this one, which is at one distance from V1 on the mid leg. Next, we move to the upper bound of beta t cube, and we see that beta t cube is less than equal to the lower bound plus m, capital M plus 1 minus L, where capital M is actually denotes the total number of major stem of the tree T. And here are some well-known cube of trees. So this is the caterpillar, and we have seen that upper bound of the caterpillar is beta t plus 3. It cannot contain any mid leg. We all know that only legs are the pendants. So lower bound can be easily get, but upper bound is, so the extra inserted vertices are already here depicted by the blue vertices. Depending on the cases that the beginning and the ending major stem contains any long leg or mid leg or not. For the above picture, you have already seen that this beginning vertex already containing a long leg, that is a which length is greater than equal to 3. So that in that case we need to insert this major stem itself and the vertex which is at 2 distance from it and the ending major stem. But for the second case, we where no long leg and mid legs are there, that is only pendants are present, then in that case we need to insert the beginning and ending major stem and the major stem and the vertex which is immediate to the beginning major stem, that is 1 distance from it. Now, next we move to the lobster tree. In case of lobster tree, it may have mid legs or long legs because it actually follows from the definition. Now, here also we have considered 2 cases, and the first case is that in where the beginning major stem contains the long leg, and the second case is that where the both the beginning and the ending vertex ending major stem contains the long legs, and in both of the cases we are able to identify the extra insertions, and it is exactly 3 in number. Next we move to the starlight tree, and where we found that beta t cube is exactly equal to beta t plus 1. Now this plus 1 is coming from for the center point. And for starlight tree, it is again the extra number of insertion is plus 2. I mean, so in there are many cases may arise here again, depending on the cases that it contains mid legs, 1 mid leg, more than 1 mid leg, or 1 long leg, or more than 1 long leg, or both. So here are all the cases are depicted here, and the blue vertices are the extra inserted vertices, red vertices are the vertices which are denoting the metric basis of t, that is the beta t in number. Now next is the deregular tree with depth t. Now deregular means every vertex has must be of degree t d, and now in this case we need to pick all the vertices in from the tth depth, I mean except one, and also we need to pick one except all the child vertices from each of the ancestor of the t minus of 2th level, that means which are blue vertices that are in t minus of 1th level, I mean. So in these cases the number is calculated here, that is beta t plus d into d minus 1 to the power of t minus 3 into d minus 2 in number for t greater than equal to 3, and for t less than equal to 2 it is beta t plus d in number. So these 2 cases are here depicted in these 2 figures. Now, next we prove that existence of a cube of t cube for every integer n satisfying beta t cube equal to n. That means if you give me any number, I can able to construct a cube of t cube for which its metric dimension should be equal to n. Now, the left hand side is for when n is odd, and the right hand side is for when n is even. And here are some restrictions we have put for the distance between v1 and v0, that is 0 modulo 3, and for other cases, I mean for v0 and w1 w2 wk else, but distances are all considered to be 1 modulo 3. Now next we have characterized those trees which are satisfying beta t cube equal to beta t and having legs as pendants. Now this but we have considered that all major stems are lying on a central path, because the general problem is very challenging and still now it is open. And in this case we see that there exist at least 3 major stems, vk1, vk2 and vk3, which are at distance 2 modulo, 1 modulo, and 0 modulo from V1. And apart from that, a second condition says that between V1 and VK1, there will be no major stem which will be 1 modulo distance from V1. And but there is no restriction between VK3 and VN we have put. But between, again, the same condition holds true for VL and VN. I mean, between VL and VN, there will be no major stem which will be at 1 modulo distance from VN, where VL is the last major stem, I mean, minimum distance major stem from VN that may have its distance, that must have its distance either will be 0 or 2 modulo 3. And the last condition says that there cannot be any major stem VM such that dt of VM VK equivalent to 1 modulo 3 for some major stem VK, and dt of VK Vj equivalent to 0 modulo 3 for all major stem VK which is right to it and within VN, I mean left to VN. Now, there are various problems that are open in this area, that is finding necessary and sufficient conditions for a tree satisfying beta t cube equal to beta t, or finding metric dimension for t to the power of r where r greater than 3. This is a general problem. And also constructing an algorithm to find out a basis, metric basis, that may also be very challenging one. Now, these are the references, and thank you. So,
Thank you, Sanchita. Any
Thank you.
questions for her from the audience? If not, let's thank her once again. And with that, we have an announcement that some of the speakers are absent. So we have the 3 more talks left in this session. And out of that, as you can see in the chat box, one of the authors has requested so that his presentation can be made earlier. So for that, I will be requesting Mohammad Yusuf Mir to present his paper now. The title of his presentation is Extension of Some Polynomial Inequalities to Rational Functions.
Good evening, sir.
Good evening.
Good evening, sir.
Yeah, you
Thank
can
you, sir.
share your screen.
Yeah. Is it visible, sir?
Yes.
Yeah, okay. Thank you, sir.
Can you make it full screen or something like that from phone? Can you make it? It's better if you rotate the screen.
Okay, sir. Now, sir, is it right now?
Yes. You can start.
Okay, sir. I am Mohammad Yusuf Mir, a research scholar in the Department of Mathematics, Central University of Kashmir. Today, I am going to present something about extension of some polynomial inequalities to rational functions. The basic idea in this paper is that we are going to generalize some polynomial inequalities. Since the rational functions are more generalized than polynomials, so this field is open. Anyone can, this is considered a hard topic presented now, to extend some polynomial inequalities to rational functions. This is the abstract of this paper. In this paper, our main focus is to extend some polynomial inequalities to rational functions. We also discuss shorter group estimates for rational functions with prescribed poles and restricted zeros in Chebyshev norm on the unit disk in the complex domain. In particular, we extend polynomial inequalities due to Dubnin, Aziz, and Dawood. This is the best terminology. We denote here the Pn. Hence, Pn denote the class of complex algebraic polynomials of the form P of z equal to summation Cjz power j, while j is running from 0 to n, of degree at most m. And P j z be the derivative of the P of z. We here write hence Rn as a set of rational functions, which is defined as the ratio of P of z by W of z, where P is the polynomial of degree n. And Wz is defined here as the product z minus Aj. And please note that here mentioned that all the poles lies outside the unit disk. So we have here mentioned mod age is greater than 1. Otherwise, we will not define this relational function, because if these poles lie inside, it may not be defined at some point. Thus, Rn is a set of rational functions with poles a1, a2, so on, an, and with finite limit at infinity. We observe that the Belsky product Bz belongs to Rn. That means Belsky product is defined here. It is also of the form Pz by Wz. So Bz is also one of the rational functions. Now, this introduction. First of all, I would like to present the result due to as Bernstein. If P belongs to Pn, then maximum taken over the modulus mod z equal to 1 mod P d z is less or equal to n times maximum mod P of z. So this gives the relation between this derivative and the polynomial itself. It actually, we can say it extremizes the polynomials. Further, Eridos and Lex has improved this inequality 1. They proved if P of z has no zeros inside a disk of radius 1, then we have this inequality 2. The Lee, Moffat, and Rodriguez were the first mathematicians who have extended these some polynomial inequalities to rational functions. They first proved if R belongs to Rn is a rational function, then for mod z equal to 1, we have this inequality 3, where B is that here knows the derivative of the Belsky product. And if Rz has no zero in a disk of radius 1, then inequality 4 holds. Recently, Govil and Mahapatra has obtained the inequalities for rational functions given as if all the zeros of a rational function R belongs to Rn lies on and outside the unit disk, then we have this inequality 5. The result is analogous to the polynomial inequality defined as if Pz has no zero in mod z less than 1, then inequality 6 holds. We first present the following refinement of inequality 6. The first result is if R is a rational function and all the zeros of a rational function lie on and outside the unit disk, then for mod R z greater than 1, we have this inequality. And equality holds if Rz is alpha Bz, where Bz is Belsky product plus beta, and with mod alpha equal to mod beta. This result is analogous to the result which is due to Aziz and Dawood, obtained by using the concept of polar derivative of the polynomials. So if we use this concept of polar derivative is defined as G alpha P of Z equal to NPZ plus alpha minus Z P dash of Z. If we use this concept, the concept of polar derivative, then we will be able to get back these polynomial inequalities from our results, which we will prove in the rational version. So our the results which we are going to prove here are more generalized than polynomials, as proved in polynomials already. Because if you use this concept of polar derivative, you will get this polynomial equality easily. This is a polynomial inequality. This inequality has already been proved by Aziz and Dawood. And for the proof of this result, we need this lemma. If R belongs to R and has all zeros on and outside the unit disk, then for mod z equal to 1, we have this inequality mod Rz is less or equal to mod R star of Z, where R star of Z is defined as Bz or 1 by Z conjugate whole conjugate. Next lemma which will be used, if R belongs to Rn and all the zeros of Rz lie on and outside the unit disk, then for mod z equal to 1, we have this inequality. And this is the proof of this theorem. Actually, due to the shortage of time, I would like to skip this proof. So I will just show this proof. This is the proof of this result, which we have proved. The next result we are going to present here. If R is a rational function of the form Pz by Wz, where Pz has been already defined as summation Cj is a polynomial of degree n greater or equal to 2, with no zeros in and inside and on a unit disk, then for mod z greater or equal to 1, we have this inequality. The beauty here is that if we use the concept of this polar derivative, we will get from this inequality, we will get the following polynomial inequality. This inequality has already been proved in polynomials. Now we have extended this the same inequality to this rational function. These are the references I have gone through this presentation. Thank you. Any questions, sir?
Thank you, Mir. Any questions for him from the audience? Okay, if not, let's thank the speaker once again. Thank you for your presentation. And we have 2 more presentations left. here. The first one which is left is to be delivered by Shubham Mukherjee. I cannot find him here in the audience list. Is it there? Shubham Mukherjee? If not, we'll pass on to the other speaker, Qazi Abu Roshan. I can see him here.
Yes, sir.
So the title of his presentation will be Extension of Gauss Circle Problem, Lattices for a Triangular Grid. Qazi Abu Roshan. Please start.
Okay. Oh, okay, so is my screen visible?
Yes, 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 yes.
Oh, okay, so is it in the slide form or?
No, it's not in the slide form. You need to click that slideshow button.
Okay.
On the top, there is a button.
I think I shared it.
No, your screen was visible, but it was not in the slide form.
Okay, so
Yeah, now it's coming.
I am Qazi Abu Roshan from Indian Association for the Cultivation of Science, and my talk is on extension of Gauss's problem in case of triangular grids. So, okay, so first of all, this is not, it is not like a technical paper, rather it is some sort of visual thing. So let me start with something which is known as Gauss's circle problem. So what was this particular thing? So it is fairly pretty known that this particular problem tells you if you have a circle, how many lattice points, that is the point x and y, where x and y are integers, how many points are there which satisfies this particular inequality. And Gauss has given us a particular formula which can actually give us this particular thing, and this particular formula can also be used to prove this Leibniz formula series for the pi. So my thinking was that is there any way to extend this particular idea in case of different types of other lattice structures, like suppose triangular lattice structures, hexagonal ones, and things like that. So from this particular thing, so I was thinking, just like I said, that what will happen for the triangular lattices. And what do I mean by triangular lattices or triangular grids? So it is some sort of structure like this. Okay, some sort of structure like this, where each of your lattices are on a particular triangle. So if I want to be a little bit more specific, then what are these particular things? So these particular things are actually a number which I can write as a plus b omega, where omega can be given by some sort of this particular expression. Okay, and these are actually the cube roots of unity, like it is shown here. So this, using this particular numbers, which are actually called Eigenstein integers, just like in case of a two-dimensional Cartesian plane, we have Gaussian integers, that is, it integers in a complex plane, it lattices in a complex plane, where a and b are actually just the integer coordinate points. Similarly, in this particular triangular grids, what we can do is we can take a and b such that these two both are integers, and we can define every possible position on this particular lattice points, integer lattice positions, using this particular formation. And this type of every possible number where a and b are integers are called Eigenstein's integers. Okay, so now the thing is, if this particular integers exist, then is it possible to define primes? Like in case of Gaussian integers, we can define Gaussian primes sort of structure. So is it possible for this one too? Like in our normal number system, it is also possible to define primes. So the thing is, indeed, we can actually do that particular thing, and this particular primes are called Einstein primes. And what are these particular primes? So similar to just our normal numbers like integers, we take unity, and if there is some number which is not divisible by any other number other than unity, then it is called prime. In the similar fashion, in our two-dimensional plane, actually, we have 6 unities, like plus minus 1, plus minus omega, and plus minus omega square. And if we have a number z which is not divisible by any other number other than this, then these are called these primes. Now, a fairly straightforward thing which we can do, and I will not show the proof here due to the short time, but the thing is, we can actually say that if a number is actually this particular class of primes or not, using this particular two simple rules, where it says that if z is actually congruent to or multiple of 3, or maybe in the form of 3m plus 1, then it can be written as in this particular structure. Other than that, it is not possible, something like that. So actually, we have primes in this particular number system, that is in particular thing. So can we actually take any integer and just factor it out in form of primes? So that was the next question. So can we factor? Actually, yes, we can very easily factor these particular things out. And if you want to factor these particular things out, you have to just be careful about 3 of these particular points. The thing is, if you have a number z, which is a plus b omega, and if it is a prime, then like it is written here, it can be factored or not depend upon how it is represented. Like z can be 3k plus 1 in the form of 3k plus 1. In that particular case, it can be actually factored into 2 of these particular primes. If it is in case of 3k plus 2, then it is not. And for the other case, that is multiple of 3, it is just written. So as a particular example, I can just show that as an example, we can take this particular number 7. And we know that it is in the form of 3 into 2 plus 1. Okay. So like there was actually a famous thing, a Fermat's law, that which tells you that if you have a number prime p, and it can be written as x square plus y square, and p is of the form 4k plus 1, then we can actually write it in this particular form. This particular two things actually are very much similar to that particular thing, where rather than 4k plus 1, we are using 3k plus 1, but exactly same type of structure. So like I am saying that 7 is 3 into 2 plus 1. So we can very easily write it as this. And you can easily see that we can actually factor it out in 2 of these particular forms, where it is very easy to see that it is actually this particular structure, which is said here. So it is, I think, completely fine. So for any type of number, it does not matter if z is just a or a plus b omega, we can always factor it out. Fine. So with keeping these particular things in point, now we can actually try to go into the main things of this particular article paper. The thing is, I will first start with an example. So let's start with a circle of radius 7. And actually, whenever you are taking a circle of radius 7, we are actually analyzing its square of that particular number, that is 49. So we can write this 49 as 7 into 7, and like I have just showed that 7 is in the form of 3k plus 1 form. So we can actually factor this out in this particular form. Fine. Now using these two particular things, then 49 can be factored as something like this. Okay, but the thing is this particular factor unique? If I arrange these particular things in a column, you can clearly see that the thing which I am getting, that is when we were analyzing 7, we are actually doing something like this. Each 7 can be factored like this, and we are getting something like this. But for the number 49, we can also rearrange it in some different way, and we will get again 2 different numbers, which are not actually primes in this particular case. But still they can be multiplied to generate 7. That is the whole idea. So this means what I can do is, this particular factorization is not unique actually. It can be clearly seen, because even if I am getting two different type of results, I can multiply one side by omega and the other side by omega square. Like I can multiply this side by omega and this side by omega square. Overall, I am not changing anything, but again, I am getting some different result. So in this particular sense, what I am saying is that it is not unique. Fine. So then can we tell that how many, if I have a number, how many lattice points are there? That is, if I go back to this previous slide, what I am actually doing is that when I am taking this number 7, what I'm actually doing is that I am drawing a circle of radius 7. And each of these particular numbers are actually the lattice points on this particular circle. So actually, if you factor this particular number out, you are actually getting the lattice points. That is the whole idea. So using the same knowledge, can we actually tell how many lattice points are generated for this case of 49? That is the radius of 7. So that particular number should be 18. So if you draw a circle of radius 7 on a triangular grid, you will get 18 lattice points. Now, why this? We just see these 3 points. That is, like I rearranged, you get 1, 7 and 2 other numbers. But where are the other numbers coming from? So if you remember, we have 6 unities in this particular case. So +1, -1, omega, minus omega, omega square, minus omega square. So each of these particular things, using simple combinatorics logic, I can say
Abu,
that
you have 2
actually
minutes
each
left.
of okay. So using this particular logic, I can just multiply with this 6 and get this lattice point number. Like it is shown here that there are actually 18 lattice points. Okay, and similarly, you can show that for a circle of square root of 7, that is for the number 7, you will get 12 lattice points. So now what we can do is, so we do this case for 3k plus 1 numbers. What about 3k plus 2 numbers? So this particular numbers, for this particular case, you will not get any sort of lattice points. Fine. And for numbers which are multiple of 3, the lattice points count does not change. What do I mean by that is, suppose you have this particular 49 or maybe the 7. If you have still 21, that is 7 times 3, or maybe 7 times any power of 3, it will not change any sort of lattice points. That is, the number will be exactly same what you are getting for the case of 7. Okay, so I will not go into the proof due to the time constraint, but these are the case. So now, keeping all of this into mind, what I can define is, I can define a number operator which is actually multiplicative, like shown here, and it is defined like this. That is, if a number is 3k plus 1, it will return 1. If it is 3k plus 2, it will define -1, and 3 to the power k, then it will be 0. Then what I can do is, I can take any number which I can actually factorize like this into normal primes. And then what I can do is, using this property, I can write this out in this sort of manner. Now, I can actually use now this particular defining feature to write this out in this sort of form. That is, Q will be actually given by this particular expression, and we can check that particular thing out. And the proofs are in the paper, so you guys can read it out. But we can check out that it actually works. So now, using this particular logic, then whatever we have done until now, that is this capital Q, it actually tells you how many lattice points are there on a circle of radius r. But what about the inside? You will just simply, the lattice points inside will be, you just divide the circle in a circle of radius 1, radius 2, and things like that. And then it will just, the total number of lattice points will be sum of this plus the origin, that is 1, something like that. And you can just break it out in a simple column type of form to see what will be the sum visually. And this will give you this particular expression. Now, if I rearrange it, then you will get this final expression, which tells you how many lattice points are there in a circle in a triangular grid. Now, the interesting thing is, using this particular idea, you can actually get a new series of pi. It is completely new and it is similar to Leibniz. And why it is similar to Leibniz? Because Leibniz's series can also be proven by same method by using just the Gaussian integers. Now you can actually use a little bit of Python code to see how this particular series converges, and these are the results. As it is pretty much clear that this particular series should converge a little bit slower than the Leibniz because it uses triangular grids. And so this is all for this particular talk.
Thank you, Abu, for your nice presentation. Any question for him? Okay, so let's thank him once again. And our next speaker will be Shubham Mukherjee. The title of his presentation is Chaotic Image Encryption Using Henan Maths. Shubham, you can present your screen.
Okay. I am asking the last speaker to please stop his presentation.
It's same. I mean, if you start sharing your screen, automatically it will start.
Good evening, everyone. First of all, I would like to thank the organizer for giving me a chance to present this work. Basically, chaotic image encryption is not very new topic at all. Basically, chaos theory is interesting fact throughout the world. Everyone knows the word butterfly effect. So what is chaos? Chaos basically measures the unpredictability of deterministic nonlinear dynamical system. This is the main fact. Around 1922, first French mathematician Hadamard introduced the system exhibiting sensitive dependence. After that, Edward Lorenz first remarked this natural phenomena around 1963. Around 1972, Lorenz conference talk became very famous. The talk title was Predictability. Does the flap of a butterfly's wing in Brazil set off a tornado in Texas? So this kind of question generated so many curiosities throughout the world. So what is chaotic system and what is the special properties? Basically, a small change in initial condition produces rapid divergence for a chaotic system. And basically chaos measures the unpredictability. And since my talk is based on encryption, so I am trying to give some short layout of cryptography. So what is cryptography? Cryptography is a powerful tool which helps us to communicate through the insecure channels. Due to the advancements of technology, we are totally bound to different kind of advancements, and we can use the encryption in case of WhatsApp chats. So cryptography is the study of secrecy and of secure communication in presence of eavesdropping adversaries. That is the main issue. And depending on different type of keys, we can categorize basic techniques as symmetric and asymmetric encryption. For example, we can consider AES, DES, RSA, Diffie-Hellman key exchange, and so many things. So what is basically chaos space image encryption, and what is the similarity between any nonlinear dynamical system and the cryptographic algorithm. In case of nonlinear dynamical system, we have some set of real numbers, and similarly, in case of cryptographic algorithm, we have finite set of integers. We have control parameters in different chaotic maps, and similarly, in case of cryptographic algorithm, we are using secret keys. There are several rounds or iteration in case of cryptographic algorithm, which is similar to several iteration in dynamical system. And basically, in case of chaos-based image encryption, we are mainly focused on two things. First one is confusion, and second one is diffusion. Confusion means we are trying to permute or rearrange the pixel values of any given image, and further we are using some secret keys to make some encryption to make the cipher image. So first of all, in this work we have used Henon map and logistic map. So what is Henon map? Basically, Michel Henon first proposed this simplified version of Lorentz attractor. So what is the nature of this map, or what is the equation? Basically, the map is defined as follows. That is, this is a recursive relation where A and B are two control parameters. So xn plus 1 is defined as follows. And with these two control parameters, the sequence either diverges or converges through a strange attractor. And in this case, we have chosen A equals to 1.4 and B equals to 0.3. So finally, we have got this kind of figure. So this is the basics of Henon map. And further, we can talk about logistic map. Renowned biologist Robert May first proposed this one-dimensional map around 1976. This is also recursive map. In this case, alpha is the control parameter which can assume the value between 1 to 4, and ln plus 1, this kind of sequence can be generated using this recursive formula. This model also depicts the complex chaos originated from simple dynamical system, and generally the value of alpha taking 3.8 shows the chaotic nature. So what's our target? Our target is to generate some chaotic sequence through this map and ultimately encrypt some image in a nice format. Around 1976, again, we have got another famous mathematician, that is Pomamu, who presented a series of works. From his work, we can choose some specific format of Henon maps. And in this case, xn and yn are defined. Oh, sorry, in this case, only xn is written, and there are three parameters: alpha, beta, and gamma. So the values of alpha, beta, gamma has been mentioned, and we have used the coupled Henon logistic map as follows, where yn is defined as a plus xn plus b plus ln, where xn coming from Henon map and ln coming from logistic map. In this case, we have considered a equals to 1.35 and b equals to 2.7, and the figure shows the time series plot of this coupled map. Basically, L. Kosarev is the first one who have introduced the notion of chaotic encryption in the public domain. Around 2001, his famous paper on IIIB magazine, which named as Chaos-Based Cryptography, a brief overview, he mentioned that chaotic cryptography seems more powerful than the traditional cryptographic protocols. Compression of data plays a vital role in digital communication, and we can also mention different type of existing literatures in this field. Arnold cat map has been used for spatial domain in encryption method proposed by Guang et al. And again, applying chain system to output signal, it was encrypted with converted image.
Shubham, are you there? Others, can you hear me?
Yes, sir.
I think Shubham is having some problem in connectivity. Shubham? I think he got disconnected. Let's wait for 1 minute. I think he got disconnected, and let's wait for 1 more minute, then we'll pass on to the next speaker. Okay, we can't wait anymore. So with that, we pass on to the last speaker for this session, Mr. Chandan Goswami.
Yes, sir.
Of his lecture is a high resilient key distribution scheme for Internet of Things security. Chandan, you can start your presentation now.
Okay, thank you. I am audible and my screen is visible.
Yes, yes, yes.
Okay, thank you. I am Chandan Goswami, research scholar, Presidency University, and now I start my today's presentation. The title of my presentation is a high resilient KP distribution scheme for the Internet of Things security. So the first question is what is Internet of Things? Basically, we all know about that. Its short form is IoT. So what is IoT? IoT means the collection, things with Internet of Things means things with internet. That is at the collective network which collective devices we connected via internet or uh, wireless or wirely. So now we going to the portion of the application of IoT. So nowadays we uh, apply directly or indirectly of internet. So here the smart health, smart home, smart road, smart spaces, industrial internet, and smart cities. So internet uses most of the things where I devices or any smart access. So for that, internet are useful. So now we shown about a worldwide connected IoT devices. So Internet of Things connected devices install base worldwide in 2015 to 2025. In billions statistics that in 2015, 15 billion approximately, and statistics given that in 2015 minimum 75 billion. So from this picture we saw that the Internet of Things devices growing exponentially. So, but every coin does have two faces. With its advancement of science and technology, at the same time, we also have seen many things. So, for that, we require IoT security. So, for given the IoT security, we going up to the cryptography viewpoint. So, cryptography is only a good to security of keys. So, secure management of keys describe the entire life cycle of keys, and keys must be pre-distributed before deployment. But we going to after the key distribution scheme with combinatorial design, and combinatorial design considerable as a suitable method due to the low overhead in the scalable key discovery phase between IoT devices. Generally, public key mechanism involve huge computational costs. So for limitation on computational capabilities, storage capacity, symmetric key mechanism are preferable. So here we show the classification of KP distribution scheme. So KP distribution methods for IoT devices, three types: generally random scheme, deterministic scheme, and hybrid scheme. And the deterministic scheme is three types: matrix based, combinatorial based, and polynomial based. We discuss here the combinatorial based KP distribution scheme. So now we give the an application of hash function. So from the picture we show that here if the 1, 2, and 9 and 6 is the four devices, and if we connect the 9 and 6 via a common key, but if we if any adversary capture this common key, then he already captured the device number 9. But if we apply the keys on the hash function, these devices is not captured. So attacks having the devices is removed for use of hash function. So now we introduce a scheme that is called base scheme. The base scheme basically we construct a symmetric matrix. So we consider a symmetric matrix with NC2 many IoT devices and the NC2 many entries, and we consider all members of the I3 of the matrix is the members of the ith group, generally denoted by group I. And from the construction of group, it is clear that intersection of two groups, distinct two groups, is exactly one element. So among all the n groups, we consider all possible order black pairs of the groups following lexicography ordering. So if we if we take the n rows and total number of IoT devices n choose 2, then the lexicography ordering n choose 2 many pair of groups we construct. And from there, a construction of base scheme. So basically, consider an n% array with fill with the numbers 1 to n choose 2, and a star means no input in that position. So give an example for n equals to 7. So for n equals to 7, network support 21 many IoT devices, n equals to 721 many IoT devices, and we consider the members of the ith row of the matrix is the members of the ith group. So from there, from this picture we show that the number of groups is 7 and maximum intersection element of 2 groups each 1. And now we consider the key construction of the base scheme. So suppose we consider a node, that means an IoT device having node ID k, and the sake of simplicity we shall refer the node as node k and the kth node. Given the node ID k, first find t and such that k lies between this and this. So for example, n equals to 7, we choose an element k equals to 15. From here we find the value of t. So keys of a node. So keys of a node is basically kth node are assigned the members union of the 2 groups and discard the node ID. So from here we here we find the keys of the ID 15. So so from these 50 lies between the group 3 and group 7. So the keys of the node 15 is group 3 union group 7. Subtract the ID 15. So these are the keys of the ID 15. And now we find out the common keys of between 2 IoT devices. The number of common keys between any pair of IoT devices is 4 or n-2. So now given 2 IoT device I and j, we find the structure of 2 common keys. So let I lies in the group x1 and group y1, and j lies in the group x2 and group y2. If x1 equals to x2, then the keys between these 2 is AXIJ union A y1 y2 having cardinality n-2, and if x1 not equals to x2 and y1 not equals to y2, then these are the common keys between the 2 devices. And if other case, if x1 not equals to x2 and y1 not equals to y2, these are also a common keys. So here is an example of common keys between 2 devices. If take the device ID 2 and device ID 9 and device ID 10, we saw that here the number of common keys either 4 or n-2, that is 5. So we saw that the number of common keys between the node ID 2 and node ID 9 is 4, and node ID 2 and node ID 10 is 4, but node ID 9 and node ID 10 common keys is 5. Now we classification methods for IoT devices. Here combinatorial design, we construct a combinatorial design related to this KP distribution scheme. So total number of IoT devices is n choose 2, that means n into n-1 by 2, and size of the key pool of IoT network is n into n-1 by 2, and the keyring size of each IoT devices is 2 into n-2, and the number of devices of each key is the same, 2 into n-2, and number of common keys between the 2 devices 4 or n-2. So now here we construct the base scheme subset. So base scheme IoT devices to be parent of the IoT devices, and assume that parent IoT devices to be in depth 1. And the next level we give one vertical hash key less than its parents. Here the parent uniformly distributed the keys to his children in such a way that each child node's keyring differs from the sibling, and maximum number of IoT devices is generated. And the parent at depth 1 will have 2 n-2 keys, and hence total 2 into n-2 depth of 2 IoT devices, and construct from a parent with keys that include all, but the parent node is in the depth 1 and the depth 2 is children of these corresponding parent nodes. And we can similarly construct the rest of the sibling of IoT devices. Again, we considering these newly generated IoT devices with a unique set of keyring of parents and construct their children at depth 3. And using the same protocol and continue so on, we get a system of network of more depths. So here is an example of base subset scheme for n equals to 7. So in depth 1, total number of nodes or IoT devices is 21, and we saw here the number of children of the node or device ID 2 is 2 into n-2, that is 10, and the number of children also the depth 2 is 2 into n-2 minus 1. So at the node ID 36, number of keys in the depth 2 is 9. So next we improve an other scheme, base scheme subset of bidirectional. So here is an improvement to gain better resiliency. We use the bidirectional hash chain of base subset. In such a case, the structure of keys in the keyring of a node depth tree changes a tuple as shown, that is this here, and these are the original setup of the base subset scheme. So these are the example of bidirectional base subset scheme. And now we going up to the what is resiliency. So resiliency is the ability of a network to continue operate in the presence of compromised IoT devices. The amount of resilience indicates how many network connections are uncompromised by capturing the number of IoT devices. So, so for that we already all know the resiliency parameter is FLS measure, where FLS is the CS by L, where C is the number of links compromised of the uncompromised IoT devices upon compromise of S random IoT devices, and L is the total number of links in the original network to count the fraction of links broken in the compromise of S IoT devices. So now we generate a resilience parameter TS. So for that TS we consider TABS. So TBS, what is TABS? For two secure connected target node IoT device A and B and given value of S, TABS measures the probability of finding as many non-restricted IoT devices to compromise all the links between A and B. And script 10 is the total number of IoT devices in the network. And target IoT devices are the two IoT devices which communication and attacker is trying to break. And capital TS is the average value of the probability of TBS overall the all possible pair of the IoT devices. So trust the definition of TS. The first is all IoT devices which compromise lead to the capture of all links between a pair of arbitrary chosen target IoT devices. Then we consider the average overall such IoT devices in the network. Therefore, from the definition, it is clear that TS gives a better understanding resiliency than FLS, but does not give the full picture of the multiple sharing situation. Therefore, we introduce a resilience measure capital TS. So these are the experimental graph. We saw that the base scheme subset is the better resiliency than the other existing scheme, some of the existing scheme. These are the references. Thank you.
Thank you, Chandan, for your nice presentation. So with that, we have come to the end of this particular session 3B. And I would like to thank all the speakers for their presentation. And I would like to invite all of you to join the main session, which is session 3A, after which we'll be having session 4 in the same link. So I am pasting the link in the chat box for session 3A, and where after that we'll be having session 4. So I would like all of you to click this link and join in session 4.